So in order to help to establish this claim, we'd like to be able to use the properties of an absolute value. And so what we are trying to do is to take this inequality, right, this claim that x is within epsilon units of the number 1, and then turn that into something that's more specific about the elements of u, because every element of u is one less than, sorry, it's a one unit fraction less than 1. So every element has the form 1 minus 1 over n. And so if we substitute that form into this absolute value, then this is what we get, right? So this is what we're trying to justify, that there exists an n for which this is the case. So now we've kind of reframed what we're trying to show. There exists a n, a natural number n, such that the absolute value of this 1 minus 1 over n minus 1 is less than epsilon. So then we come inside the absolute value and we simplify what we have. And in here, the 1 minus 1 cancel one another out, right? So that what we're left with is the absolute value of minus 1 over n is less than epsilon. Then what happens to this minus? It goes away. Because after all, the properties of absolute value tell us that if we have a negative 1 multiplied by 1 over n on the inside of the parentheses, we can break that apart into the absolute value of negative 1 times the absolute value of 1 over n. But the absolute value of negative 1 is 1. And so the minus sign can be seen to just kind of vanish. So now we have a slightly simpler inequality. We're trying to solve this inequality to get n by itself. So what did you do from here? First of all, how do we deal with the absolute value? Yeah, how do we know that the absolute value is irrelevant here? Right. And because n's a natural number, in particular, n is greater than 0. And therefore, 1 over n is greater than 0. And therefore, its absolute value is equal to itself on the nose by definition of absolute value. So we have 1 over n is less than epsilon. So then what do we do from here? We just have to, take a reciprocal on both sides. And the key here is when I take a reciprocal on both sides, what happens to my inequality? Yeah, it switches. Because, thinking sort of in calculus terms, the function f of t equals 1 over t, the reciprocal function, is a decreasing function. If you look at the graph, y equals 1 over x, it has a downward slope everywhere. Right? And so since it's a decreasing function, when I apply it to both sides of an inequality, the inequality reverses. And so we get this statement, n is greater than 1 over epsilon. So now the last thing I want to ask before I turn you back into your teams is, how do we know that there exists such an n? Why does such an n exist? Because all we've done so far is rearrange our inequality. We haven't said why that inequality is actually satisfied by some natural number n. Well, why is that true? Archimedes! Yes, by Archimedes. What did the Archimedes principle say again? The natural numbers don't have an upper bound. So whatever 1 over epsilon is, I can round it to the nearest natural number, and I know that I can find a natural number that's even bigger than that by the Archimedes principle, right? So here's Archimedes coming in to help us. It shows us that not only can we rewrite this inequality, but that we can actually argue that this inequality is satisfied by some natural number n. And therefore, there is some element in the set U that satisfies this inequality. So now, those are all the pieces for your proof. And then the last portion of this sheet is just to actually put those pieces in an order that makes sense to somebody reading the proof.